Hello, in this video I'm going to think about and work through a proof for the formula for the sum of an arithmetic series. Actually it's worth prefacing my comments working in this video that there are a number of ways to arrive at such a proof. In this video I want to talk in particular about a method often attributed to Gauss, and actually there's a really nice, it's a nice enough story I suppose that goes along with it about young Gauss, and that story is that in junior school his teacher, who I believe was named J.G. Butner, set out a task or a challenge to his students, which of course included Gauss, to add up the integers from 1 to 100. And the story goes that young Gauss was able to produce an answer within moments. And how he did so is quite smart. Actually perhaps it's maybe at the start of this video, just think about how he was able to find that sum, because it does lead directly to a proof for the formula for the sum of an arithmetic series. And so, as I said, Gauss was handed the task or the challenge to find the sum, the integers from 1 to 100. So we could write, we would just write that out: 1 plus 2 plus 3 plus 4 plus 5 plus ... and we'll just say plus 99 plus 100, right? And so Gauss looked at this, he said okay, and how he was able to work it out is he said, well, what if we let s equal the integers from 1 to 100? So s equals, just say as written above, 1 plus 2 plus 3 plus 4 plus 5 plus, and we'll just go ... plus 98 plus 99 plus 100. Okay, and he said, well, what if we reverse the sum? So what if we let s equal 1, and we work back from 100 to 1? So we could say s equals 100 plus 99 plus 98 plus 97 plus ... we'll just say 3 plus 2 plus 1. And we could label this s sub 1 or s sub 2 if we wanted. It's not really necessary at this point, but and what Gauss did reportedly is he essentially added the two sums. So we would get s plus s, which would give us 2s, and notice interestingly enough that if you add the two sums, right, 1 plus 2 plus 3 plus 4 all the way to 100, and 100 plus 99 plus 98 plus 97 all the way to 1, you get, well, 1 plus 100. You can think about it this way: 1 plus 100 is 101. 2 plus 99 is, well, 101. 4 plus 90, or 3 plus 98 is 101. 4 plus 97 is 101, and so on. And so what we end up getting is, well, 101 plus 101 plus 101, right? And of course there are going to be 100 of these, and so we could simplify in our next line, and we could just say, well, okay, 2s equals 100 times 101. And now what Gauss reportedly did is he said, okay, well, this is now really just simple algebra, isn't it? At this point we want to solve for s, so let's divide both sides by 2, and we get s equals 100 times 100, 101, 101 over 2, which happens to equal 5,050. And so Gauss found the sum. And I suppose what's really interesting about this is that we can think about why this works or why this is the case. We can think more deeply, and we arrive at a proof for the formula for the sum of an arithmetic series. And so, let's do that now. But actually, before we get to the actual proof, and it might even be possible that I work on it on the right hand side here. If I provide my working here on the right, if I just divide this page like so, I might have enough space. Now, it's important, maybe it's worthwhile of just prefacing the proof and thinking about this working here on the left more deeply. To preface, it's by just pointing out or highlighting that an arithmetic series is formed by adding together the terms of an arithmetic sequence. For example, u sub 1 plus u sub 2 plus u sub 3 plus ... all the way to u sub n, right? So the pattern is so it's quite obvious, right? So an arithmetic series is formed by adding together the terms of an arithmetic series as such. However, in an arithmetic series, and I'll just erase this to avoid confusion because we're talking about arithmetic series. In an arithmetic series, the next term is found by adding or subtracting a constant number. That constant number is often called, is denoted with a D. It's often called the common difference, and the first term is often denoted with an A. And so, therefore, we can all arithmetic series can be put in the form A plus D plus A plus 2D, A plus 2D plus A plus 3D, A plus 3D, and so just write one more, plus A plus 4D, and so on. Now, what's important to notice, I suppose what's really important to notice here is the relationship between the number of the term in this series and the coefficient of D. So let's just say, so A is the first term, D is the second term, right? So I'll just write second, just write 2. A plus 2D is the third term, A plus 3D is the fourth term, A plus 4D is the fifth term. So notice, A plus 3D, that's the fourth term. It's not the third term, it's the fourth term. And so in general, we can write it this way. How about we write it this way? You can say that S sub n equals, so maybe it's best to word it this way, that in general, the nth, we can use this fact, really. Notice the relationship between the terms and the coefficient of D and so on. We can use these facts to produce a formula for the nth term of an arithmetic series. And the nth term of an arithmetic series is, well, S, we can write it this way, S sub n equals the sum, where we can write R equals 0, n of A plus n minus 1 D. Okay, and this is a very common statement. I believe actually one will probably one I think first learns all of this at A level or equivalent. But where A is of course the first term, D is the common difference, right? And in saying all of that, we can now sort of move toward the actual proof. And in short, we can say, okay, well, I'm working through working on the left here, talking about Gauss and how he found the sum, the integers from 1 to 100. Well, okay, we can say in general, and all of this sort of comes to fit together here, where we can say in general, S sub n equals, well, we already know what it equals. We've written it up here. In general, it's a plus d plus a plus 2d, a plus 2d, plus, we can say dot dot dot, plus a plus, and then in brackets, n minus 2d, right, it's the second last term, plus a plus, and then again in brackets, n minus 1 d, which is the last term. And reversing the sum, as Gauss did here, so this general statement, the first line, s sub n, you can think about here as the first line in Gauss's work when he went to produce his answer. And so in reversing, in reversing the sum, as we did in the second line here on the left, we can write s sub n equals, or what does it equal? The first term is going to be a plus n minus 1 d. I'm writing somewhat small, I'm doing my best effort to sort of fit all of this into the space. And the second term, of course, then is going to be brackets a plus n minus 2 d. And the third term, I'm sure the pattern is quite obvious at this point. It's going to be a plus n minus 3 d plus, and I'm running out of space, so I'll stop here. I'll go plus dot 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 plus a plus d, a plus d plus a. Right, so we've just reversed the sum here on the second line, just as we did on the left hand side here. We reversed the sum 100 to plus 99 all the way to 1, where in the first line it was 1 to 100. Right, so it's the exact same thing here on the right, although written generally. And so again, if we, just as we did on the left, if we add the two sums, we get 2s sub n equals a 2a, I'll use square brackets here, 2a, right, 2a plus n minus 1 d, close that off, square brackets, and then the second term we get 2a, and it happens to be the case where, just as we think of it very practically, just as when one adds the two sums here on the left hand side, we've got 101 plus 101 plus 101 plus 101, and so on and so on. Well, here we get, when we add up the sum of these two, right, when we add these two sums up, I should say, we get 2a plus n minus 1d plus 2a plus n minus 1d plus n minus 1d plus, and I don't know if I need to I'll keep going, I'll write a couple more. It's going to be again plus 2a plus n minus 1d plus n minus 1d, square brackets, and okay, I'll just bring it back down here, dot 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 plus dot dot dot, and plus 2a is the last term, 2a plus n minus 1d plus n minus 1 times d, like so. And so I suppose what's really curious about this, if you think about it, is that, well, okay, we've written it very generally here, right? We have s sub n, and so we could say, well, we could write this furthermore, that it's just going to be 2a plus n minus 1d plus 2a plus n minus 1d plus 2a plus n minus 1d, on and on and on and on, right? However many terms, and so, well, n amount of terms, in fact. So we can rewrite this, we can simplify it by saying 2s sub n equals n times 2a plus n minus 1, and I'll just put that in brackets, n minus 1d. and there are n lots of 2a plus n minus 1d. And so from there, just as we did here, well, now it's just simple algebra. We can think, okay, well, we want to solve for s of n. We divide by 2, and thus 1 arrives at the formula for the sum of arithmetic series. It's n over 2 times 2a plus n minus 1d, which is very cool. And it's I suppose fun to think about it in relation to Gauss's answer and his junior school days, and I mean, you could even point out here before concluding this video that, so if this is the formula for the sum of an arithmetic series, we can also say, or we can also write a little bit differently. We can say, or s sub n equals n over 2 times a plus, and it's usually denoted with a capital L, which is the last term of the series. And so again, a is the first term, d is the common difference up here, and in this case, L is the last term in the series.